You're welcome to today's edition of Subject Math. Today we'll be talking about set theory. Now, talking about set theory, we're going to cover a lot under set theory, from set theory down to Venn diagram and solving serious questions from your WAEC past question. So let's proceed with set theory. Now, talking about set theory. Now, what gets to come to your head? What do you get to think of? First and foremost, the definition of set. Now, set is defined as the collection. Please note, set is defined as a collection of well-defined objects. I'd like us to note, so your set is defined as a collection of well-defined objects. Now, if I ask you for a set of kitchen utensils, so a set of kitchen utensils is your pot, your stove, your gas burner, what else? Your spoon, your knives, etc. Now, this is a set of kitchen utensils. Now, if I should have a house here or have a phone in this set, now it is no longer well defined. Imagine a set of kitchen utensils and you're having trousers. It is no longer defined. Now, so talking about set, it has to do with what? Defined objects. So collection of this thing called the defined object. So this collection of well-defined objects, I made mention of kitchen utensils. Now, here the kitchen itself is a universal set. Now, I'd like us to universal set here is a set notation. Now, a universal set is a set that carries all the elements of a set. So if I say the set of kitchen utensils, now that set that carries all the whole kitchen utensil, is known as something called your universal set. Now, in this universal set, then we have various subsets, but I'm going to explain what a subset is to you when we get to set notation. But let's take it slowly, a step at a time. Now, having your set of everything in the kitchen to be a universal set, now I want to explain to you that each unit, whenever I say each unit, I mean that particular thing. Everything in particular you have in your kitchen. Everything in particular you have in your kitchen is clear and it's known as what? Element of a set. So each unit or each content of your set is known or called your element. Now, talking about set notation. Now, a set notation is terminologies used in set. For example, which I said something like your universal set. So your universal set here, universal set is known as the mother of all sets. Now, when I say the mother of all sets, it simply means that every element, every subset is drawn out from the universal set. Now, if I say, what is a set of all food? What is a set of food? If I ask you for the set of food, we're going to be having rice, beans, yam, um, flour, etc. Now, this is a set of all food. Now, if I should bring out the set of carbohydrates, if I bring out the set of proteinous food, etc. Now, everything I'm going to bring out is going to be coming from the set of all food. So anything I bring out from it, if I say set of carbohydrates, if I say set of carbohydrates and I said rice, yam, etc. Now, if I say set of protein, set of proteinous food, say beans, soya beans, plantain, etc. Now, look at, if you pay attention, this set of carbohydrate was brought out from the set of food, the set of protein was brought out from the set of food. Now, since these two were brought out, they were brought out from a general set. Now, this general set here is the mother of all sets, because everything we are talking about food has to be brought out, you have to bring them out from the set of food. Now, having your set of carbohydrates, your set of protein, now these are subsets. These are subsets of your universal set. Why are they called subsets? They are subsets because they were brought out, they were break out, they were reduced, or they were picked from your mother of all sets. Now, going further, there's what we call empty set. Now, empty set is a set that has no content. When I say it has no content, I mean your empty set has no element. For example, a set of all father that can breastfeed their child. A set of all men or all father that can breastfeed their child. Now look at this set. This set there's actually no father that can breastfeed their child. So this is going to give an empty set. Call it an empty set is known as a null set. You can call it a null set. You can either use this to represent it, or you can use this to represent it. An empty set. So, pay close attention to this. Pay close attention to this. So, an empty set has no content. An empty set has no element. So, if I ask you, what is the set of all bag that can talk? Okay, so the question is, can any bag talk at all? No, this is not bag could talk. What does that mean? It becomes an empty set. I hope you're understanding what I'm trying to explain. So, explaining this with a note, now I have here universal set. So the universal set is the mother of all sets, like I explained, from where other sets are drawn, and it's denoted by E. It's denoted by this. Use this to denote your universal set, or use your big U to denote your universal set. Now let's take up an example. E.g., your universal set of what? Universal set of all students in Unilag. Now, all students in Unilag. Now we have a subset. Subset here says all science students. Now, do you see all science students are part of students that are in Unilag? All education students. Now, all education students are also part of students in Unilag, and all faculty of arts students. All faculty of arts students are also a set of students in Unilag. Now, did you notice that set A, set B, and set C were all drawn out from this particular set. And because of they were able to be drawn out from this particular set, that is how we call this, or that's why this all students in Unilag is called the mother set. And so your mother set here is your universal set. Now, null set. A null or empty set. Now, this is a set. This is a set that contains no element. Whenever your set contains no element at all, it is known or called an empty or null set. So an empty set is a set of every set. Please let us note. An empty set is a subset of every set. So no matter the set you're having, an empty set is a subset. That is, you can bring out an empty set from every set. Now, this empty set is denoted by phi or empty set without anything. Now, some students do make mistake and say, whenever they ask to denote an empty set, they write something like this. Now, please, this is not an empty set. This is not an empty. So this is what? A set of elements 0. So this is a set. This is a set with an element 0, and 0 is a number. So, now for example, x is equal to Unilag student who is a VC. Now look at this. A Unilag student, or rather, a Unilag student cannot be a VC at the same time. So, a set of a Unilag student who is a VC. So, a Unilag student cannot be a VC and study at the same time. For example, you watching this video, a set of a student who is a principal. Listen to that. A set of a student who is a principal. A student cannot be a principal and also study at the same time. I believe you are understanding what I'm trying to say. So, you ask such kind of question, a student who is a principal is going to give you a null set or an empty set. Now, going further, we have subset. Now, the subset is best known as the children of a universal set. The subset is best known as children. Why am I calling children? I'm calling children because the subset is brought or picked from the word universal set. That is why I best describe it as a child. I best describe it as the children of your universal set. So look at, we have our universal set in Roman numeral from 1, 2, 3, 4, 5, 6, 7. Now, the first subset here is II, which is 2. We have 4, we have 6. So 2, 4, 6. Now, what is the next subset? 1, 3, 5, 7. Now, A here, A is a subset of U. That is, A is brought out from U, denoted by, now this is what you use to denote your subset, or this. So therefore you can say that A is a subset of U, or you can say B is a subset of your universal set. So that sign there is a sign to denote your universal set. Power set. Now, the power set is bringing together of all subsets of a particular set. And this power set is the aim is to generate and bring these subsets together. So it is set bx, then the power of the set is denoted by 2 raised to the power x. Now, note that your x here is the cardinality of your set. When I say cardinality is what? The individual count of the element of a set. If you have a set like this that says 2 5, 7, 9. If I ask for the cardinality is the individual count of elements. So this is 1, 2, 3, 4. So the cardinality of this set is 4. Now, so find the power set of 2, 4, 6. So the power set here becomes 2 raised to power x. Here x is the cardinality. So the cardinality here is 3. 1, 2, 3. So 2 raised to power 3 is 8. Therefore, the power set becomes, so the power set here becomes the subset of this particular set. So the subset here is what? 1, the first, an empty set. Another subset is 2, 4, 6. Another subset is here is 2, 4, 6, 2, 4, 2, 6, 4, 6. Now if you count 1, 2, 3, 4, 5, 6, 7, 8, it gave us what? The number of what? 8, just like what our power set gave us. So whenever you have or you're asked to find the power set, after evaluating its cardinality, then you want to re-express the subset, the possible subset of that particular set. So this one gave us a, these are the possible, or these are the what? Subset of the particular what? Set 2, 4, 6. So no matter anytime you want to pick up subsets, the subset of this particular set can never be beyond this particular 8 subsets which have been given to us. So this particular 8 subsets that have been given to us here is known as the power set. Now, equal set. Now, a set or sets are said to be equal. So these sets are said to be equal if they have the same element, irrespective of their arrangement. Now, whenever sets have the same element, but different arrangement, no matter how you want to arrange it, but they have the same element, identical element. Now, you have this is set A here 1, 2, 3, 4, 5. You have set B here 2, 3, 1, 4, 5. And you have set C, first 5 numbers of the numeral. Now, set D 1, 2, 3, 4, 5, 6. Now, conclusively, A is equal to set A is equal to set B is equal to set C. Now, this is a conclusion, but set A is equal to set B, but they are not equal to set D. Why are they not equal to set D? Because set D is having an extra element. What is the extra element of set D? 6. So, because of this 6, it is not making the sets equal. So, equal sets are sets that have same elements irrespective of their arrangement. Now, equivalent set. I have a set which says, equivalent set here says that if 2 or more sets are equivalent, then they have the same number of elements. Now, when they say this set have the same number of elements, we're not paying attention to the particular elements if they are identical, but the same number. When I say the same number, I mean the same cardinality. The same cardinality. So whenever 2 sets have the same cardinality, then that sets are known to be what? Equivalent set. An equivalent set is denoted by this sign. Now look at this. Set A is equal to x, y, z. Set B is equal to 1, 2, 3. Now, set A is equivalent to set B because every element in set A could pair. Every element in set A can pair to another element in set B. Look at their pairing. Look at their pairing. Look at their pairing. Therefore, since they can pair themselves, that is conclusively or Conclusively, we can say that what set A and B is an equivalent set. So I'd like us to pay close attention to it. They don't need to have identical elements. So far they can pair themselves. Therefore, it is equivalent set. But if they cannot pair themselves, the set cannot be tagged equivalent set. Cardinality of a set. Now, the cardinality of a set, this is the number of elements in a particular set. The total number of elements or the head count of elements individually. When I say head count, I mean you are counting the elements one after the other in a particular set, and it is denoted by number of sets. So if the set is A is equal to, so it becomes number of A. If the set is M, it becomes what? Number of F. So this is how you denote your cardinality. So here you have what? A is equal to 1, 2, 3, 4, x. So we are asked to find cardinality, that is, number of A is equal to, what is the total count? 1, 2, 3, 4, 5. So your cardinality of the set here is equal to 5. So when it's equal to 5, you have it clearly there as to be our final answer. Union. Now, the union of a set, first and foremost, I would like us to know that the union of a set is denoted with a U. So please notice this. The union of your set is denoted with something like U. Now, any explanation, the union of this set is just like marriage between two sets, two or more sets. So it's just like what? Marriage. When I say marriage, it means the coming together of two or more sets. Now, explaining further, now when I say it's like marriage, here I mean it's what the coming together of elements. What did I say? Coming together of element. I would like us to note the word coming together of element of a set without repeating. Now these are the key words. Coming together of element without repeating. So when I say coming together, you don't need to bring even though they are coming together, you're not bringing every particular thing or repeating one particular element 5 times or 6 times or thereabout. You just pick that particular element. Now I have an example here that says that A is equal to 1, 2, 3, 5, 4, 5, and 6. And I have now my B here is 5, 10, 15, and 20. I ask you to find A union B. That is, find the marriage that exists between A and B. So what is the marriage that exists between A and B? 1, 2, 3, 4. Now, I have 5 here, I have 5 here. Since I have 5, I'll treat both of them as 1. I have my 6, I have 10, I have 15, I have 20. So at this junction, 1, 2, 3, 5, 4, 5, 6, 10, 15, 20. So the fusion of these two subsets makes a union. Now going further, we have our intersection. So clearly our intersection is denoted by n. Is n like? So here, the intersection of a set is the common elements. Now the key word here is common element. The common element in a particular set, and it is denoted by your n. So if A and B are two sets mathematically, you can say that A intersection B is equal to X is in A and S is in B. Now this interpretation is S such that S is an element of A and S is an element of B. So interpreting this thing, S is such that S is an element of A and S is an element of B. So this particular interpretation, that's what we have here. So now, I have an example here, which we want to treat the example. An example on intersection for us to know what intersection looks like. Now, it said clearly This, I'd like us to pay attention. Look at this question. This question has lower bound and upper bound. Now, having lower bound and upper bound, what do I mean? Now, it says here that S is such that 2 is less than or equal to S. Is less than or equal to S is what? Less than 16. Is what? Prime. Now, look at this. This in here has lower bound and it has what? Upper bound. So this interpretation here means that A is equal to, it said S such that is what? 2 is less than or equal to. So the number stands for what? 2 and what? Less than or equal to what? X, which becomes now. So don't forget, this interpretation says what? Prime. Prime here means something. Now let's pick every number from 2 to 16, which becomes 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now please pay attention. The question has here is what? Less than 16. So I'm going to stop in the number less than 16, which is what? 15. And whenever you say prime, prime simply means what? Every number that can divide itself and 1. So let us circle every number that can divide itself and 1 here. 2, 3, 5, 7, 11, and 13. Now that's our prime numbers. So they say what? S is such that what? S is prime. So this becomes 2, 3, 5, 7, 11, and 13. Now here, this becomes that. Now, please don't forget the definition. So prime here, prime numbers, please note, are numbers that has no factor. It can be divided only by itself and 1. So these numbers, they cannot be reduced by any other number, only itself and 1. So 2, 3, 5, 7, 11, and 13. So going further, the number here says Q here says Q is equal to X such that what? S is less than or equal to S, which is less than or equal to, okay, we're supposed to have a bound here. So going forward, so 2, which is less than or equal to X, which is less than or equal to what? 16. That is, our bound here, and don't forget it says that what? X is what? Odd. It simply means every odd number between 2 and 16. Let's note the number between 2 and 16. That's 2, 3, 4, 5. Okay, we'll have this 15 and then finally what? 16. Let's note every odd numbers. We have 3, 5, 7, 9, 11, 13, and we have what? 15. Now, so these are our odd numbers. 3, odd numbers we have here. 3 are 5, 7, 9, 11, 13, and 15. Now, what does the question say? The question says find A intersection Q, which is what? What does what A and Q have in common? So what does they have in common? They have 3 in common. What else do they have in common? They have 5 in common. What else? 7 in common. 11 in common. And 13 in common. Therefore, your A intersection Q is going to give you 3, 5, 7, 11, and 13 as your final answer. Complement of a set. Now, please note, the complement of a set is a set that has everything. Okay? It has everything not present. It has everything not present in a particular subset, but in the universal set or the mother set. Now, let me take a quick example. If my universal set is 1, 2, 3, 4, 5, and I have a set A which is 2, 4, 6. Now, complement of this set means what? Everything not present in this particular set. So what are everything not present in this particular set but in the universal set? This cancels this cancels this, right? What are everything not present? That everything not present here becomes complement. A complement is equal to, the A complement here is equal to 1, 3, and 5. So that's your complement. So your complement is denoted by x raised to the power this or x raised to the power c. Please, your x there is dummy variable, which means what? Any alphabet can replace it depending on what? The set. Now, so universal set minus what? X. Universal set minus x will give you your complement. So if I say my universal set here minus what? A. Universal set minus A, this cancels, it gives me what? My what? My A complement. And what is my A complement? My A complement here is 1, 3, and 5. So what an example here? If what? If my universal set is equal to 5, 10, 15, 20, 25, 30, then x here is equal to 1, so x is equal to 10, 20, 30. So what is x complement? X complement means what? Means your universal set minus x. Universal set minus x, which is going to give you what? S complement. Now what is this S complement? What it's what your universal set minus your S. So this becomes, this cancels this cancels this, and this cancels this. So your S complement, the S complement here is now equal to 5, 15, and 25. So this is your X complement, and that's your final answer. Going further, finite set. Now, a finite set is any set that is countable. Example, number of students in the classroom. So the number of students in your classroom can be determined. Therefore, it is a finite what? Set. Now, infinite set, they are uncountable sets. For example, list of all negative numbers. If I ask you to list every negative number for me, wow. You are therefore starting from what? -1 to minus infinity. Now, an infinity is undeterminate. You cannot determine infinity. So, -1 to negative infinity cannot be counted. So, a set of all negative numbers cannot be counted. So, I go for that. A disjoint set. A disjoint set is a set that has nothing in common. Whenever two sets has nothing in common, that set is known to be a disjoint set. And the intersection of a disjoint set is a null set. I told you that a null set is an empty set. So if I should tell you what is the intersection of set of animals and set of numbers, so there's no correlation between a set of animals and a set of what? Number. Therefore, it is what? A null or an empty set. Now, going further to the laws of sets. Now, the first law here is the idempotent law. And the idempotent law says that A union A is equal to A. So as A intersection A is going to give you A. So this is your idempotent law. Now, going further to your associative law, A union, open bracket, B union C is equal to A union B union A, okay, union what? C. That goes further to say that what A intersection B, A intersection open bracket B intersection C is equal to A intersection B intersection C. Now that is your associative law. Now going further to your commutative law. So your commutative law says A union B is the same thing as B union A, and A intersection B is going to give you the same as B intersection A. Either ways, no matter how you switch them, they're going to give you the same answer. So that goes further to your distributive law. And your distributive law says that A intersection open bracket B union C is going to give you A intersection B, then your union A intersection C. Likewise, A union open bracket B intersection C, that's going to give you your what? A union B, then you have your intersection A union C. So these are what? The first four basic laws of set, and we're going to proceed with more of the laws of set. Going further now to the what? Other what? Laws of set. So I have what? De Morgan's law, and De Morgan's law here states that A union B complement is equal to A complement intersection B complement. In that same hand, it says that A intersection B complement is equal to A complement union B complement. So this is what De Morgan's law states. So going further to what complement law says. So complement law says A complement is going to give you what? A. When your complement cancels each other, gives you your A. And that also says that what? Your universal or mother set complement is equal to the null set. So the complement of a universal set is going to give you an empty set, because the universal set is not under any particular set. So that goes going further. So A union A complement is going to give you your universal set. So what? Your A union, your A complement, that's the coming together of your complement and the A. Both of them coming together will give you your universal set. So A intersection A complement. So if looking for what's the complement of a set and the set has in common, definitely they have what? Nothing in common, which is what? An empty set. So if you look for what? Complement of a null set, complement of an empty set will give you what? A universal set. So going further to what? Your identity law. So identity law here becomes that what? A union empty set is going to give you A. So if you are bringing together an empty set and your A together, it's going to give you what? A. So A intersection, your A intersection, your A intersection, your universal set. So looking for what your A and your universal set has together is going to give you A, because after merging your A and universal set, it's just going to merge only what is in A, which will give you what? Your A. So and for your union, not intersection this time, the union, that is the coming together of your A and your what? Your A and your universal set is going to give you your universal set. Because this time around, the universal set covers everything that is in A. So when I say union, don't forget, I said that union has to do with the marriage of two different sets. So the coming together of your A union, your E gives you your E, and what? Your A intersection, an empty set. An empty set, sorry, A intersection empty set now is going to give you what? An empty set, because the coming together of A and intersection, that is what they have in common with an empty set. Definitely there's nothing they have in common. So since they have nothing in common, that gives you an empty set. So with this, let's begin to take questions which you are going to deal with. So example here says, if what x is such that 2 less than x 2 less than or equal to x is less than what? 16. So that becomes here that what? Now this here, please pay close attention. A here is equal to that. It says that A here is equal to 2 is less than x and 2 is less than or equal to x. which is less than 16, which is prime numbers. Don't forget, prime numbers are numbers that doesn't have factors. This we have here prime numbers between, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And picking our prime numbers here, we have what? 2, 3, 5, 7, 11, 10, and what? And 13. And our Q here says, P, this P please. Our Q here says, what does our Q says? That what? 2 is less than equal to S is less than equal to what? 13. Where S is what? Odd numbers. So odd numbers between what? 2 and 13. So what are the odd numbers between 2 and 13? That are what? 3, 5, 7, 9, 11, and 13. Now what does this question say? The question said what? Cardinality of P union Q. First and foremost, what is P union Q? P union what? Q. P union Q is equal to what? P union Q means what? The coming together of P and Q, that is 2, 3, 2, 3, 5, 7, 9, 11, and 13. And the next one is what? Now what is the cardinality? Cardinality is number of P union Q. The number of P union Q is 1, 2, 3, 4, 5, 6, 7. 7. Okay. Now what is the next? P intersection Q. P intersection Q means well, what P and Q have in common. What does P and Q have in common? Let's note them. They have what? They have 3 in common. What else do they have in common? They have what? 5. What else? They have 7. What else? They have 11. And they have what? 13. Now, so going further, cardinality of P intersection Q is equal to 1, 2, 3, 4, 5. 5. So what does the question say? The question says find cardinality of P union Q. P union Q here is 7 plus cardinality of P intersection Q. P intersection Q is 5. So 7 plus 5 here is going to give us a positive number 12. So this one question, the solution here gives us 12. So going further, we have this question here. The question here says, given that P is equal to 1, A, B, 3, 5, what is the power set of P? Solution. Power set, so the power set of P is equal to 2 raised to power P. Therefore, this is now 2 raised to power. What is the cardinality of P? 1, 2, 3, 4, 5. That is equal to 32. Now, if you want to express your P, if you want to express the 32 subset, which is the power here, you can express your 32 subset in this form. You have 1, let's use the black marker. You have 1, you have A, you have B, you have 3, you have 5, you have 1, A, B, 3, 5, you have 1 A, you have 1 have 1 comma 3, you have 1 comma 5. So this is how we're going to be having them. Now, if you notice, we're asked to find what? The power, the power of set P. Now, we got it, and our value here is what? 32. Please, now this is the answer for your NECO. Your answer there is 32 straight out. But now, I want to use it as an example further. So I wanted to give you the whole layout of subsets, possible subsets that can come under this particular expression. They said the power set is what? 32, and these are the 32 subsets. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. So we've been able to see the 32 possible subsets that could come under this particular power of set P. Now, look at this question that M and N are two subsets of a universal set U if M is what? If M is what? A subset of N, find what? M intersection N complement. Now, this means that what? M to N means that N has elements in M. Therefore, M intersection N complement is equal to, since N has elements in N, since M intersection N complement is going to give you M complement, because N has what? Element in N. So going further, M intersection, open bracket, M intersection N complement. Now, this gave us M complement. So M intersection M complement. M intersection M complement, they have nothing in common. So M intersection M complement is going to give you a null set or an empty set. And that is our final answer for this particular NECO quiz. Yeah. Now look at this question from work. I'd like us to attempt. We're going to say that if what A is equal to what x comma y such that y squared is equal to 4 raised to power x, and B is equal to x comma y such that y raised to power x is equal to 16, find the element of A intersection B. So this is the solution. So from here you have that what y squared is equal to 4 raised to power x. So this square comes over, turns to square root, as y is equal to what? Square root of 4 raised to power x. So this becomes that y here is equal to 4 raised to power x in bracket, your square root turns to 1 over 2, power of 1 over 2. So y here is equal to 4 raised to power x over 2. 4 raised to power x over 2, I call this equation 1. So taking from B, so B says that what y raised to power x is equal to 16. Call this equation number 2. So at this junction, equating equation 1 and 2. Now, so taking this equation 1, putting it into this place, equation 1 here says that y is equal to this, equation 2 says that this, and this is the same as now. Instead of putting equation 1 into equation 2, this becomes that what? 4x over 2. This is y. Then don't forget the s that came with the division 2. X is equal to what? 16. So I think expanding this is now what? 4 raised to power x over 2 is equal to what? 16. So at this junction, you can now say what? 2 raised to power what? X times x gives us what? X squared over 2. So 2 raised to power 2 times what? X squared over 2 is equal to 2 raised to power 4. So at this junction, 2 cancels 2. So if your 2 cancels your 2 cancels your 2, you're left with what? 2 raised to power x squared is equal to 2 raised to power 4. So equating basis. So x squared is equal to 4. This comes over. So x is equal to plus or minus square root of 4. So x is equal to plus or minus 2. So since your x is equal to plus or minus 2, recall the expression that says that what? Y raised to power 2 is equal to 4 raised to power x. So since we got this particular expression, so let's say when x is equal to 2. So when x is equal to 2, this becomes now y is equal to square root of 4 raised to power x, which becomes now y is equal to square root of what? 4 raised to power 2. This cancels out, so y is equal to 4. Y is equal to what? 4. So let's go. When x is equal to minus 2, when x is equal to minus 2, so what happens? When x is equal to minus 2, this becomes y is equal to square root of 4 raised to power minus 2. So this becomes y is equal to square root of 1 over 4 raised to power 2. So y here is equal to square root of 1 over 4. Therefore, a here is equal to when a here is equal to, so when x is equal to, when your x is equal to 2, positive 2, your y is equal to, your y is equal to 4. Okay, so when x is equal to, when your x is equal to minus 2, your y is equal to 1 over 4. So this is the same thing for A, and this is also the same thing for B. So conclusive, so when x is equal to 2, y is equal to 4. So when x is equal to minus 2, y is equal to 1 over 4. Therefore, in conclusion, we have our answer as x is equal to 2, y is equal to 4, or x is equal to minus 2, and y is equal to 1 over 4. Attention. Now you have a wire question here that says you show that the Morgan's law is true. Given that the universal set is this, and P is equal to this, Q is equal to this, then show that what? The Morgan's law is true. And don't forget, when I was trying to tell you about the Morgan's law and various laws, I explained the Morgan's law, which says that P union Q complement is equal to P complement intersection Q complement. So we have to prove that this is true from this particular expression. Now, from this particular expression, we have that P is equal to 1, 2, 4, 6, and 10. I also have that Q is equal to 2, 3, 6, and 9. Therefore, P union Q becomes 1, 2, 3, 4, 6, 9, 10. So therefore, P union Q complement is now this away from this. So we have 1 cancel 1, 2 cancel 2, 3 cancel 3, 4 cancel 4, no 5, 5, 6 cancel 6, 6 cancel 6, okay, no 7, no 8, 9 cancel 9, 10 cancel 10. So at this junction, this becomes your P union Q complement. But that's not all. That's not all. Now we have what? P P complement. P complement is equal to what? P complement. This cancels this. 2 cancel 2. Okay, now there's no 3. We have 3. 4 cancel 4. There's no 5. 6 cancel 6. There's no 7. 8 cancel no 8. No 9. So then 10 cancel 10. Now they say, then what is your Q complement? Q complement is equal to, what's your Q complement? Q complement, Q complement. 2 cancel 2, we have 1. 3 cancel 3. Okay, no 4. No 5. 6 cancel 6. No 7. No 8. 9 cancel 9. 10. No 10. So at this junction, they have what? P complement intersection what? Q complement. That is what both of them have in common. What does both of them have in common? What do they have in common? They have 5 in common. They have 5 in common. They have 7 in common. They have 7 in common. What else do they have? They have 8 in common. Therefore, P union Q complement gave you 5, 7, 8. P complement intersection Q complement gave you 5, 7, 8. Therefore, left hand side is equal to right hand side. De Morgan's theorem. So I would rather say conclusively, De Morgan's theorem, De Morgan's law is true. And that is your final answer. Conclusively, De Morgan's law is true for the evaluation. Now, going further, we're going to be talking about Venn diagram. So now, what is this thing called Venn diagram? Venn diagram is a representation of sets in shapes, whereby subsets are represented by circles, while rectangle enclosing the circles represents universal set. Now, so Venn diagram is where you get to use what? Rectangle to express your what? Your information. Now they say what? Subsets are represented by circles. So subsets here are represented by circles. While what? The rectangle enclosing them is known as the universal set. So we have the subset A and B. So we have this now. So going further now, we're going to be explaining the various shades or the shading pattern of what? Of Venn diagram. So let's talk about the shading patterns of the Venn diagram. Now going further, so Venn diagram shading. So look at, if you notice, this was shaded all through external. So this is your A. So this is your A shaded, so this is what? A prime was shaded, so all these places is your what? A complement or A prime. So A prime was not shaded, and this is your A. And this is your intersection, this is your union, this is diagrammatic. Now this is your when your A is shaded, the value of A. This is your A union B complement, and this is your A complement intersection B. This is your A intersection B intersection C. This is your A, B, and your C. So now having seen the diagrammatic representation of or the diagrammatic Venn diagram shading, now let's begin to take what various examples to back up what we've what explained so far on the board. Now look at this question, paying close attention to it. Okay, the question says out of 400 students in the final year, so let's represent the question. Out of 400 students, so your universal set here is equal to 400 students. Out of 400 students in the final year in the secondary school, 300 are offering biology and 190 are offering chemistry. So I'll talk about two courses here. 300 are offering biology, so biology here. We're talking about 300 and okay, and 180 are offering so chemistry 190. Now 300 are offering biology and 190 are offering chemistry. So they said how many students are offering both? So let both be x. If both is x, now this becomes 300 minus x and 190 minus x. So in total now this becomes 300 minus x plus 190 minus x is equal to the total student, which is 400. Now why am I minusing x? Because this is a full circle and the number of students offering both are considered to be what? 70. But let's read out the question. The question said, how many students are offering both biology and chemistry? If only 70 are offering neither biology nor chemistry. That is, if only 70 are offering neither biology, so if 70 are not offering, so this 70 goes down here, goes down there, plus 70 is equal to 400. So at this junction, you add up, adding up, you have 300 plus 190 plus 70. That's going to give you 560. And this is plus y plus x minus s plus s cancel. So you have 560 minus s is equal to 400. So collecting like terms, so minus x here is equal to 400 minus 560. So minus s here is equal to 160. So x here is equal to what? Minus 160. So divide by both side by minus 1. So x here is equal to 160. So since your x here is equal to 160, they said how many students are offering at least one of biology or chemistry? How many students are offering one of biology or chemistry now? So this goes further to be the question says how many are offering one of biology or chemistry. So talking about student that offers biology, so number of biology is equal to 300 minus x, and your x is now what? 160. That is 300 minus 160 will give the number that offers biology. So 300 minus 160, and that is equal to 140. The number that offers chemistry is equal to 190 minus x, that is equal to 190 minus 160, that is equal to 30. So therefore, the number of students that offer biology is 140, and the number of students that offer chemistry is 30. So going further, so when they say students that offer chemistry or biology, I say number of students that offer chemistry or biology, that's going to give you the addition of. So talking about the summation there, the summation of number of students that study biology plus number of students that study chemistry plus number of students that study B intersection C. And that is because number of students that study biology is 140 plus 30 plus 160. So the addition, you add 140 plus 30 plus 160. That's going to give you 330 students as your final answer. The 330 students study at least one course or one subject. Now, pay attention to this question. So the question says, a hotel, the breakfast menu is a choice between yam or plantain or both. The Venn diagram shows the choice made by 25 guests of the hotel. Now find the value of x. Now this is for plantain, this is for yam. So this becomes, and the total here becomes 2x plus 1 plus x plus x minus 2 raised to the power 2 is equal to 25. Therefore, 2x plus 1 plus x plus, expanding this, x squared minus 4x minus what plus 4 is equal to 25. So at this junction, collecting like terms, this is x squared, 2x, 3x minus 4x, that's going to give us minus x. We have 1 here, 1 plus 4, that's 5, plus 5, this comes over minus 25 is equal to 0. So x squared minus x minus 20 is equal to 0. So we have a quadratic equation here. Now, so having a quadratic equation here, so let's proceed. Now, we have to solve this by factorization. What are the factors? Minus 5 and 4. So x squared minus 5x plus 4x minus 20 is equal to 0. What is common here? X. So x minus 5. What is common here? Plus 4 here, x minus 5 is equal to 20. So x plus 4, x minus 5 is equal to 0. So at this junction, x plus 4 is equal to 0, or x minus 5 is equal to 0. So proceeding here, x is equal to minus 4, or x is equal to 5. Therefore, since you are having minus 4, you have to let minus 4 go because of the negative sign, and we're going to continue solving with the value of 5. So therefore, the value of I here says the value of x is equal to 5. Now the next one says, what is the probability that a guest chooses at random? A guest choosing at random chooses only one of the two. Now, since the next question said find the probability that a guest choosing at random chooses only one of the two. So this becomes, first of all, that is plantain's value. Don't forget that's 2 times 5 plus 1, that is equals to 11. And yeah, that is equals to what? 5 minus 2 squared, that is equal to 5 minus 2, that's 3. 3 squared equals to what? 9. Now don't forget, total guest is equal to what? 25. So they say if choosing a random, like you choose this one, so that is what? If the person chooses plantain, probability of choosing plantain is equal to what? 11 over 25. And what? Probability of choosing yam is equal to 9 over 25. Therefore, at this junction, so the probability of what? Choosing any one of the two, probability of what? Choosing any one of the two becomes 11 over 25 plus 9 over 25. Here our LCM there is 25. So 25 divided by 25, 1 times 11 plus 25 divided by 25, 1 times 9, that equals 11 plus 9, that equals 20 over 25. So 5 here, 4, 5 here, 5. That is equal to 4 over 5. So the probability of choosing any one is equal to 4 over 5. So conclusively, we now have our exercise. So you have to try them out. Your answers are given in green. The answers are marked in green. So you try them out and practice enough questions as possible.